on complex numbers, right? The real number system, that is the number system, as we know today, is a result of gradually development in uh, as natural numbers, that is 1, 2, 3, 4, okay, and these are positive integers, okay, uh, we use for counting, okay, and uh, if a and b are the natural numbers, the sum of a plus b and the product will be a into b, okay, or also a natural number. And there are negative integers and zeros, right, which are and zeros. Okay, so which are denoted by that is -1, -2, -3, okay, and 0. Permit solutions of equations such as that is x plus b is equal to a, where a and b are the natural numbers. So this leads to the operation of subtraction or inverse of addition, okay, or we write this as x is equal to a minus b. Also, integers are closed under the operation of addition, multiplication, and subtraction. Also, we have rational numbers such as 3 by 4 minus 8 by 3. Okay, these permit solutions of equation as bx is equal to a. For all integers, uh, that is a and b, where b is not equal to 0. Now this leads to the operation of division or inverse of multiplication, and we write this as x is equal to a divided by b, okay, where um, the quotient of a and b, okay, where a is in the numerator and b is in the denominator. We have irrational numbers, okay, such as √2 and pi, that cannot be expressed in the form of a by b, and where a and b are the integers and b is not equal to 0. Okay. The complex number system, that is that there is no real number x that satisfies the polynomial equation, which is x square plus 1, okay, x square plus 1 is equal to 0. So this permits this permits solution of this and the similar equations to a set of complex numbers. Okay, so we can consider a complex number as having the form a plus bi, where a and b are real numbers, are real numbers, and I is I, which is called an imaginary unit, imaginary unit, has the property that is I square, which is equal to minus 1, I square, which is minus 1. Now, if z is a plus bi, okay, then a is the real part of z, and b is the imaginary part of z, and are denoted by uh, re curly braces z, and I am curly braces z. Okay, uh, the symbol z, which can stand for a complex number or a complex variable, complex variable. Okay,
B D I.
yeah, b minus d I, yeah, so that's it. So the real part and the imaginary part, very easy. Okay, so multiplication and division, right? Okay, so we'll look into absolute value. So absolute value or modulus, okay, of a complex number a plus bi, okay, is defined as mod a plus bi, which is square root of a square plus b square. So this is the example for finding the modulus of a complex number. Okay, now uh, if z1, z2, z3, zn are complex numbers, okay, the following properties hold. Okay, the these are very important properties which hold. That is z1, z2, which is equal to mod of z1 mod of z2. Okay, or we can, if we have n m number of those, so that will be multiplied again, that will be z1 z2 mod of particular one. Okay, and also we have another property which is z1 by z2, which is equal to mod of the same, right? So Z1 by Z2. Okay, individually mod. We can put that also. So if Z2 is not equal to 0, okay, and we have one more property, that is Z1 plus Z2, which is less than or equal to mod of Z1 plus mod of Z2, okay, or with respect to m terms, so that will be Z1, Z2, Z3 and Zm, okay, less than or equal to Z1, Z2, right, plus Cm, okay. And also we have another property, which is Z1 mod of Z1 plus or minus Z2, which is greater than or equal to mod of Z1 minus mod of Z2. Okay, so please remember these properties. So we have one more Eyeless formula.
Yeah.
By assuming that the infinite expansion e to the power of x, which is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on, of the elementary calculus, when x is equal to I theta. So this is e to the power of I theta. Okay, so you get cos theta plus I sin theta. Okay, which is called the Euler's formula. Okay, it is more convenient, however, if we uh, uh, take as e to the power of I theta cos theta plus I sin theta. In a general, we define as e to the power of z, which is e to the power of x plus iy. Okay, e to the power of x plus man, if you multiply this, so cos y plus I sin y. Okay, so in special case, if y is equal to 0, then it is reduces to e to the power of x. Okay, so please remember this. And also for the uh, de Moivre's theorem, it reduces to e to the power of I theta to the power of n, which is equal to e to the power of I n theta. Okay, I square, I cube, I power 4, I power 5, and I power 6. Okay, okay, fine then. Yeah, okay, we shall find this. So z as 2 minus 3i. Okay, z bar is the conjugate of it. So 2 plus 3i. Okay, and mod of z square is 2 square plus minus 3 whole square, which is equal to 13. Okay, and therefore the multiplicative inverse of is given by z inverse, which is z bar by mod c square. Okay, or uh, which is 2 plus 3i by 13. Okay, so when you separate with real and imaginary, so that will be 2 by 13 plus 3 by 13i. Okay, so this will be the multiplicative inverse. So, so that would be taking this as the given one. Now the denominator one, the conjugate, multiply and divide by 1 plus root 2i. Okay, 1 plus root 2i. Right. So you get this as 5 plus 5 root 2i plus root 2i minus 2 divided by 1 minus root 2i whole square. Okay, so which further simplification you would get as 1 plus 2 root 2i. Okay,
Yes, sir.
yeah. Also, let us find I to the power of minus 35. Okay, this is 1 by I to the power of 35. Okay, and we know that I square and to the power of the 17. So because 17 into 2 is 34, right? And I is still left, so that will be 35, right? So I square is minus 1. So to the power of 17 will be minus. So you'll get in the denominator as minus I. Again, multiply and I, right? So which will lead to I.